All right. I'm going to get started in just a second talking about capacitors. I just want to double check real quick. Who in this room has designed a circuit with a capacitor in it? Okay, that's so weird. I would have never thought that that would happen. Okay, I'm going to get started because, like I usually do, I have more stuff than I have time to talk about. For those that don't know me, I have about a decade of experience in the passive component industry. I used to work for a capacitor company. If you guess which one, tomorrow night at the party, I'll buy you a beer. So what I wanted to talk about is how do you choose the right capacitor when you have multiple options. And so I'm going to talk about multiple dielectrics and try to give you a couple of things to think about every time you have to make a decision. And where this came from, and the reason I do talks about capacitors is because they're a deceptively complex device. It seems like it's just two terminals, conductive terminals separated by a dielectric material. And if you know the dielectric constant, or the permittivity more correctly, of that dielectric material, the surface area of those electrodes, and then the distance between them, you'll know the amount of capacitance that that device has. However, as you guys have probably noticed, knowing the amount of capacitance you need is not enough to choose a capacitor. And part of the reason why is if we go and look at somebody like Octopart, they have 2.3 million capacitor part numbers. So it kind of makes you want to ask the question of, well, then how do I pick the right capacitor for whatever I'm doing? 2.3 million makes it sound like it's going to be really hard. Turns out it's actually super easy to pick the right capacitor for every application every single time. All it takes is 2 words. It depends. It depends on what you're doing and what trade-offs you're willing to take or willing to make. So there's probably about a dozen types of capacitor dielectrics out there with multiple variations upon those. But I group them into basically these 5. I'm going to try to talk about 4 of these 5. We may not get to film, but we'll see if we can get that far. I also forgot, if you have questions, feel free to ask while I'm going. If I say I'll get to that in a minute, and then it sounds like I forgot, please feel free to ask me again. Okay. How many people have ever used a ceramic capacitor before? Right? Yeah, they're the most popular type. So what are they? They are sheets of a ceramic material, typically barium titanate, that have a metal electrode screen printed on top of them, typically nickel, and then there's multiple layers of those stacked on top of each other, hence the name multi-layer ceramic capacitor. There are 4 ways that a ceramic capacitor loses capacitance. The first one is the easiest. It's the tolerance band and the tolerance bending from manufacturing. And by the way, the higher you go up in capacitance, the less Gaussian that curve becomes. So even if it's supposed to be plus or minus 20%, it's almost never plus. The temperature coefficient is another way that they can lose capacitance, and this is actually pretty well defined. In fact, it's probably the second thing you'll look for when you're looking for a capacitor, like on a distributor website. The 3 letters each mean something, and there's a table you can find on the internet that fully explains that. I'm going to come back to that in a minute. There's also an aging effect with ceramic capacitors. Ceramics will lose about, class 2 ceramics will lose about 3% of their capacitance per decade hour. So 1, 10, 100, 1,000, 100,000 after they've been through the reflow oven. So regardless of whether or not you apply voltage to them, they are constantly losing capacitance over time. But after 1,000 hours, you're talking on the order of years. And it's a very well-defined characteristic. Now, the most famous and the one that is the worst and the one that we're going to talk about is applying voltage to a capacitor. Who knows about the voltage coefficient or DC bias effect of ceramics? Oh, wow. Okay, I'm sorry. So I'm going to show you a slide, but I wanted to express how you make this type of measurement. So I borrowed a impedance analyzer from Hioki, which has a DC bias voltage unit connected to a power supply. So I can apply a wide range of DC voltages to a capacitor. Now, this section I am talking about ceramic capacitors. Astute viewers will notice that that is not a ceramic capacitor. I just didn't have a good picture that had all 4 elements in it. So basically with this measurement, you apply a signal, and then you go through and you apply a test signal, and then you apply a DC bias to that signal. This is kind of an eye chart. I just wanted you to know how much work I did to get to this graph, which is my favorite graph. This is a real part, a real measurement. I actually did this. So it's a 0805 X7R, the best class 2 dielectric you can get, 22 microfarad capacitor rated for 10 volts. With 0 volt DC bias, it measured about 21 microfarads. So it's well within its tolerance band. After applying 5 volts to this 10 volt capacitor, it dropped to about 6.7 microfarads. So half the applied voltage, and the capacitance is well below half of its rated capacitance. At 10 volts, if you have the audacity to apply 10 volts to this 10 volt rated capacitor, you lose 86% of its capacitance. Literally, you just move the decimal point over. It's only like 2.3, maybe 3 microfarads. And this is really critical because this is something that capacitor manufacturers will tell you happen. They will give you typical charts for their parts, but finding this information on a part-by-part basis is extremely difficult and time-consuming. But you need to understand and know about it. You know, the old adage of, oh, derate capacitors by 50%, well, the reason you do it for ceramics is not to extend their lifetime. It's to get more effective capacitance out of them. Now, I wanted to give you a couple of guidelines because I think when you first start to realize how bad this is, then the next question is, well, how do I pick the right capacitor? So fundamentally, because this whole thing happens because of a fundamental property of the barium titanate. And it turns out as that dielectric layer gets thinner, the voltage coefficient gets worse. So anything that makes the dielectric thinner compared to another capacitor is going to be worse. It's going to have a worse voltage coefficient. So the first one's pretty easy. It's voltage. Two capacitors with different rated voltages. The one with the lower rated voltage has a thinner dielectric, so it will have a worse voltage coefficient. That's why whenever I pick ceramics, you always pick the highest voltage you can get. The other one, and this isn't necessarily this is more like of a secondary effect. The temperature coefficient can also be an indicator of the effective thickness. And what I mean by that is if you look at a X7R versus an X5R, so let's say you have the same capacitance, the same voltage, and the same case size, and the only difference is one is X5R, rated for 85 degrees C, and one is X7R, rated for 125 degrees C, the X7R is going to have a thicker dielectric. That's how it got its higher temperature coefficient or temperature rating. So it's going to have a better voltage coefficient compared to an X5R. And then this last one, and if you can wrap your mind around this, then you'll actually start to realize how easy it is to kind of pick a ceramic cap. As you downsize, say you go from an 0805 to an 0603, you are effectively reducing, not even effectively, you are reducing the surface area of those dielectric plates. If you reduce the surface area to have the same capacitance in a similar, or to have the same capacitance, you now need more layers. The problem is you can't stack the layers higher than the part is long. That's the fundamental limit of how high you can stack a cap. And so manufacturers will then start to figure out how can we reduce the thickness of the layers so that we can continue to make 1 microfarad capacitors. So there's really 3 things they can do. The first one is they just push their materials properties to the limits, and they just make it as thin as they possibly can. The second one is they reduce the voltage rating or they reduce the temperature coefficient. That's why if you see like a 10 microfarad 0805, that's X7R, you will almost never see from the same manufacturer an 0603, 10 microfarad, that's rated X7R. It's almost always going to be X5R, or there's going to be a jump in rated voltage. The key here is as you get smaller, the layers are getting thinner. So what you need to realize is if you decide to go to a smaller case size, you will not get more capacitance out of a smaller case size than a larger case size. It's just not going to happen. I'm going to skip that. Just real quick, it's not all bad. If you have less than a kilohertz of AC signals, you can actually get more capacitance. But after about a kilohertz, the AC effect goes away. Ironically, it's related to the reason that there's a DC bias effect in the first place. So when picking ceramics, I typically know what case sizes I'm going to use because of where they're going on the board. So the first thing I do is try to filter by X7R, and from there I look for what is the highest rated voltage for the amount of capacitance that I need. Sometimes I'll swap that and I'll do, okay, well, I'll go for the highest rated voltage I can get and then go for the smallest case size from there. But those are the three things you kind of have to play with to decide which ceramic capacitor makes the most sense. Okay, before I move on to the next dielectric, any questions? Great. So aluminum electrolytic capacitors, I think this is what probably everybody thinks of when they think of capacitors. These are two aluminum foils separated by a piece of paper that gets saturated with an electrolyte. The electrolyte provides electrical conductivity from what is the actual cathode layer of the dielectric layer to the cathode foil. The electrolyte also dominates the ESR characteristics of an electrolytic, which also dominates the lifetime capability of the electrolytic. So usually with an electrolytic, you're usually just saying, okay, well, I've got a certain amount of space, so what's the biggest cap I can get? And what the real decision comes down to is, well, this cap's rated for 1,000 hours, another cap is rated for 5,000 hours. How do you decide between those based on their lifetime? All wet electrolytics will wear out eventually. So for example, this cap is rated for 1,000 hours at 105 degrees C. Now, this does not mean at 1,000 hours and 1 second, the cap will fail and explode. Instead, what it means is after you've exposed it to full rated voltage at full rated temperature for 1,000 hours, either the capacitance, the dissipation factor, or the leakage current are going to shift outside of a set value. And so it's called a parametric wear out or a parametric fail, which means the capacitor is still mostly functional, but it's no longer operating within its defined specs. So that's where this 1,000 hours for, well, pretty much everything comes from. Now, you might be thinking, well, wait a minute. I use 1,000 hour rated caps all the time, and my stuff lasts more than a month. So what's going on? Thanks to Arrhenius, if you decrease the operational temperature 10 degrees, you double the life. So if you have a 105 degree rated capacitor, and let's say you operate it at 95 degrees C, which is ambient plus the self-heating, you'll double the life. And if you get down to more benign temperatures, now you're into tens of thousands of hours. And then also, if you do some voltage derating, you get some accelerated or some benefit there as well. Okay. So that's something to just something to keep in mind is if you can get. Okay. Let me hold on. Now, there's another thing you can do to reduce the heat issue. There is an alternative aluminum electrolytic, which is made with a polymer material instead of an electrolyte. And so these are solid capacitors that have a conductive material that connect the cathode layer to the cathode foil. The key thing with these guys is that it's highly conductive, and so it has a significantly lower ESR. ESR is going to generate heat when you run some ripple current through the part. So by using a polymer, you can reduce the amount of heat, self-heating that the part creates. You also get less ripple voltage because it's lower ESR, and you also get wider frequency response. I just wanted to point out I found two parts that are the same can size, same voltage, same capacitance, but there's 2 ohms of ESR on the traditional and like 20 milliohms on the polymer. It's usually more like 1 order of magnitude, but still, it's significantly less than a traditional electrolytic. The other point I was going to make too is when you use polymer instead, because of the lower ESR, you get better frequency response. So this is like, I think it's like 50 kilohertz versus 20 kilohertz for the same part before it resonates. Also, the impedance graph of the electrolytic looks more like a ceramic than a traditional electrolytic. Okay, so for electrolytics, usually you know how much area you have, and you basically just want as much capacitance as you can get. Personally, I start with temperature. If I'm designing for something that has an 85 degree C spec, I almost always look at 105 rated parts, and then I go and see what I can get. If I can't, then I'll go back down to 85 C. One caution I will give you is if you start to say, well, I can get 125 degrees C, and then in my 60 degree application, I'll get way more life out of it. That is probably true, but as you go up in temperature rating, the ESR of those parts tends to go up with them as well. So you'll just end up self-heating more, which kind of negates the point of going to a 125. So just something else to watch out for. But to me, the thing to watch out for in electrolytics is what's their operational life, and the easiest way to manage that is look at their operating temperature. Okay? Okay. Who has heard of a supercapacitor? Okay, hold on. Keep your hands up. Now, how many of you knew that it's a trademark name? Yeah. So NEC, well, actually, NEC, their passive component division in the 1970s, trademarked the name. I think today the trademark is expired, so it's why everybody can use it. But they're actually electrical double layer capacitors, or EDLCs. So I'm only going to talk about one specific type, which are these radial style. And the reason I want to talk about these is because a lot of people want to replace batteries with something that looks like this. Because, hey, it's a capacitor, so you can just put it in and it'll work fine. And from a spec point of view, they're fantastic. They have massive current carrying capabilities. They have like tens to hundreds of milliohms of ESR. But they're only rated for 2.5 to 3 volts. Anything that's an EDLC fundamentally is going to have a voltage limit around 3 volts or less. I won't get into why, but this chart is a cross-section. The white line on the 2 terminals is called a Helmholtz layer, and it forms when an electric field is applied to the capacitor. It's between the interface of the activated carbon terminal and the liquid electrolyte. That layer is incredibly thin, which is why you get so much capacitance out of these devices. But it's also why individual cells are only rated for a couple of volts. Now, here's the thing you have to be careful when you're trying to use a supercapacitor, especially in replace of a battery. They are capacitors. They store energy electrostatically. If you use that 10 farad part that I just showed, it is a dead short when it's discharged. So here, my top waveform is the voltage across the capacitor, and the bottom is the current. And the thing you'll notice is as soon as I turn it on, there's a huge inductive spike, and then it takes, I think it's like 30 seconds for the cap to charge up. And it's because I current limited the power supply to 500 milliamps. And then after it gets really close to being fully charged, then it sort of has a charge that looks kind of like what you normally see with a traditional capacitor. The reason I point this out is because you really have to think about how are you going to charge this cap when it's dead. You can't just put it behind a solar panel and think the solar panel will ever be able to charge it up. It can't. You have to have some kind of charge controller. The other thing to watch out for is that 10 farads looks really impressive. It does look really impressive, but I didn't do the math. 2.5 farads is really impressive because if you charge that to 5 volts, that's about 36 joules of energy inside the cap. For all caps, this equation is true. You take 1/2 the capacitance times the voltage squared. That's how much energy is stored in the capacitor. The problem is you don't get access to all of it. Because that assumes you're going to discharge the cap to 0 volts. Anyone ever design a circuit that works at 0 volts? Right? So what you end up having to do is calculate what is the energy going to be at the time your circuit drops out, because that's all that's usable. So like in this case, it ends up being 31 joules. So we lose, let's just call it 15% of what's available in the cap just because our circuit can't make use of it. Okay, so I don't consider this necessarily a design problem, but this is one of those things I see trip up people all the time because they think, oh, well, I've got 100 farads, so I have this much energy. Well, yes, that's true, but you can't use it. And then the last thing, I didn't have a slide for this, but these kind of cells, they typically have acetonitrile as their electrolyte. They do have a charge limit. You can only fully discharge and recharge them about 500,000 times. So it's better than a battery, but I just want to be clear that they are not solid-state devices. Eventually, they'll parametrically fail as well. Okay? Okay, let me ask this question. Is anyone designing anything that plugs into the wall? Like you're designing something on the AC main side? Okay. I want to mention this. There's lots I could talk about on film caps, but this is the biggest mistake I see people make, and I think it's an important one to be aware of. So this is a simple AC to DC converter. All EMI filters have capacitors. Because of where they're located, they're called a X capacitor or a Y capacitor. These are specifically designed to fail safely because, most people don't like to buy stuff that causes death. It's really hard to undo. So there are actual safety ratings associated with those caps, especially the Y caps, because they're usually connected between the AC line and the chassis. One of the biggest mistakes I've seen people make is they want to get rid of all of that big, clunky, like transformer and rectifier bridge and all that, and build what's called a capacitive dropper, or I call it a series dropper, where you're connected directly to AC mains with an LDO or some other lightweight circuit. And in there is a coupling capacitor. The problem I see is a ton of people will use an X2 rated capacitor for that application. One, because they're super cheap, and two, because they come with a ton of these agency approval stamps all over them. They have all these things. They're UL rated, they're IEC rated, they're 6384 rated, blah, blah, blah. It doesn't matter, though, because those ratings only apply when the cap is used as an EMI suppressor. Using it as a series dropper, none other than UL 94, none of the safety recs are valid. So it's like a fool's errand to say, oh, this is UL approved, so that's why we're going to use it. UL won't approve the design because it's incorrectly used. Also, and this is a dirty secret that that big capacitor doesn't want you to know, when does EMI testing occur for a product? What part of the production cycle? Does it happen before the product ships or after the product ships? You get your EMI, you get your FCC cert before the product ships. Nobody cares if the EMI filter stops working 10 years later. Also, and this is actually intentional, these capacitors are connected to line and typically also to something metal in the design. They are designed to wear out very quickly. And if you use them as a series dropper where you're putting a boatload of current through them, they'll wear out in 2 to 3 years. They are not designed to carry a heavy load. They're meant to be EMI suppressors. So all I'm going to say there is for film caps, only use the film, look at the data sheet and see what application it's meant for because there's a reason they're saying certain applications. Okay. Yeah. Yeah. Yeah, the question is if they don't, the reason they don't care that it works after 10 years is because they don't care. I'm being a little bit facetious, but the reality is, yeah. I mean, the caps are actually still doing what they were supposed to do. They're supposed to wear themselves out because in theory, you could say it got hit with a bunch of transients and it wore out, and that's okay. But yeah, I mean, nobody goes, and I've never heard of a product losing its FCC cert 10 years later because its EMI filter wore out. All right, I'm going to show this QR code and then the URL again. I just wanted to mention I put together a bunch of stuff. So all the videos I've done on capacitors, links to the simulation tools for Murata and Kemet. Earlier I said it's really hard to get the VCC data for capacitors. Those two tools do provide some of that data. Some of them do a better job than others. Also, some of them are all math and no measurement. So, but at least the tools are there and it's better than nothing. The Circuit Break podcast, which used to be the Macrofab podcast, just 2 weeks ago, Stephen and Parker talked about VCC specifically. And so since it just happened like 2 weeks ago, I thought I'd mention it. This was not one that I was involved in, but I did come on their podcast a couple years ago to talk about something similar. I'm also trying to put together some kind of chart or tool to try to help explain some of these things, and I don't think this is it. So if you have ideas on how to do that, I would love to hear them because I'd like a way to explain this kind of stuff more simply. I mean, in the past, I used to conduct 2-day seminars on everything we just talked about, and it's really hard to find that balance. So, all right, with that, any questions? And if not, I'm here all weekend, so it's really easy to get me to talk about caps. What caps have the safest failure modes? Film caps. Film caps are basically, you think of them as layers of saran wrap that have metal that's been vapor deposited on top of it. So it's a really, really thin metallization. And so anytime there's a damage in the dielectric, it creates a short, and that short actually causes the plastic to melt. And there's so much more plastic than metal that it basically effectively disconnects the fault site. And so they actually fail open. It is extremely difficult to get a film cap to fail short. I mean, other than when you put a nail through it, then it's really easy. Actually, I take that back. It's not. True story. I tried to make a trade show exhibit where we would do that, and the lawyers just said no. Like, no. There's no plexiglass thick enough to let you do that. All right. Any other questions? All right, guys. Thank you.